Hi. So as I was thinking about how to teach the subject of dielectrics, it occurred to me that this is a rather extremely tricky subject to deal with, let alone teach. So my plan is to go through this as slowly as possible, and also as carefully as possible, in the hope that there will be as little miscommunication as there can be with through this online lecture. So if you have any questions and uncertainties about what I teach online, you can always post your questions on the Q&A segment of the iCampus, or you can just email me with questions and I'll try to produce a video containing my answers and responses to your questions and queries. So let's try to have some feedback and back and forth between the students and myself, even though we're not directly connected in the same physical space. I guess we just have to make the best out of this situation in whatever way we can. Okay, so electric field creates electric polarization in all forms of matter, whether it is dielectric, whether it is an insulator, or a metal, or a biological organism. This is an obvious fact. Now, one can define this vector called the polarization, which measures the degree of electric dipole moments that are induced by the external electric field. And the relation can be expressed in terms of this linear relation between the polarization vector P and electric field vector E. Okay. And let me label the proportionality constant as kappa. I think actually this is not the most common way of writing kappa. This is the most common way. And the reason why we have these dielectric constant in front is that if we do that, then we can make this kappa thing dimensionless. And when you have a dimensionless number, it's good because when this dimensionless number is big, then you can say that the material with a large kappa is a highly polarizable matter, whereas the material with small kappa will be a less polarizable matter. Okay, so every material actually has a characteristic kappa. And interestingly, a metal can be thought of as a dielectric material that has a divergent kappa. So it's a rather extreme form of a dielectric. And the reason why we can think of this as an infinite kappa material is the following. When we apply an electric field to a piece of metal like this, then the negative charge basically flies off to infinity on its left, and while the positive charge flies off to the infinity toward the direction of the electric field, and the negative charge flies off in the direction opposite to the electric field. So there's no limit on how far these charges can fly off in response to the electric field. And the only limitation really comes from the boundary of the material. So that's why these charges tend to sit on the surface of the metallic material because there's nowhere else to go once you have reached the surface. Okay, in such a case, this dipole moment which is a product of the charge times the separation between positive and negative charge, diverges because this separation becomes divergent. Okay, so the polarization is, in a sense, infinite, which would only be true if, in this relation, we took this kappa, the polarizability, to be infinite. Okay, so this is one way of defining what a metal is. It's a dielectric with infinite polarizability. Um, the reason why in insulators we don't have an infinite polarizability, rather a finite value, is because charges are bound. Charges are bound to the atomic nucleus, so it can move slightly from the equilibrium position, but that's about all. So for the bound charges, the maximum response they can develop under the electric field is to create some dipole moment. And the degree of the dipole moment that is developed in response to the electric field is captured by this constant kappa, which is called the polarizability. Okay, so last time I tried to show that the divergence of this polarization vector with a negative sign is equal to some sort of charge density, which is induced as a result of the inhomogeneity in the polarization vector. And a simple way of illustrating that physics is through this diagram where all the p vectors are pointing toward the same origin. And in terms of a picture, in terms of the charge distribution, that means the positive charges get accumulated near the origin like this. So obviously, in this region, you have an excess of positive charges, while the divergence of the polarization vector, because the polarization vectors are pointing inwards like this, would be a negative value. So this presence of negative sign here makes sense according to this picture. Okay, so it seems pretty clear, at least from this picture, that inhomogeneity in the polarization leads to some sort of local charge accumulation or local charge depletion. You just have to reverse the sign direction of the arrows in this plot, and then you'll see that in the center you will have an accumulation of negative charges, which will be a charge depletion. Okay, but another way of thinking about this equation is you can take this as a definition of the polarization vector P. So to make sense out of this relation, which is somehow given to us through some sort of plausibility argument or heuristic reasoning, you can play around with it. Actually, you have to play around with it to develop some physical intuition for what this equation really means. In this case, the way to play around with it is to do some integrals. First of all, let's do some integral of this divergence of the polarization vector, like that. Now, this is a classic example where you can apply the Gauss theorem to convert the volume integral to the surface integral. So S stands for the Gaussian surface, and then you have to integrate this flux over the entire area of the surface. Okay, so now if this relation was true, then this surface integral in turn equals to. Sorry, I should have put a minus sign here because there should have been a minus sign over here. So then this surface integral over here, uh, surface integral over here should be equal to minus the integral, volume integral of the polarization charge density, which would give me the total polarization charge with a minus sign for that dielectric material. Okay, but we know that in applying the Gauss theorem to convert the surface integral, the volume integral to the surface integral, we can choose any surface we want as long as it's convenient for us to perform the surface integral at the end of the day. So then my suggestion is to choose the surface which is way outside the boundaries of the dielectric material itself. Okay, so this shaded region is a piece of dielectric matter, and this shaded region is the Gaussian surface on which I'm going to perform the surface integration. But since we're far outside the dielectric material, there will be no polarization, and therefore this surface integral seems nicely equal to 0, which means that the total polarization charge inside that dielectric matter is always 0. Now, in some sense, this is making sense because you can imagine the polarized dielectric matter in this way. Well, if you have an accumulation of positive charges all around the surface of the dielectric, then there will be equal and opposite amount of negative charges that accumulate somewhere deep inside the dielectric matter. So there's as many positive charges as there are negative charges, which gives us the total charge equal to 0. So this claim that the total polarization charge must equal to 0 does seem to make sense. Okay, however, in a couple of minutes, I will show you that this argument actually has a flaw, and that one should be more careful in applying Gauss theorem type of argument to situations like this. Okay, so with that in mind, let me just skip this and move to the next theme, which is the question: what happens if we integrate not the divergence of the polarization vector, but the polarization vector itself? What is the volume integral of the polarization vector? That's the question. Of course, we don't know much about the nature of this polarization vector, so we don't have any good feeling for what the answer might be. To address that question, you can start by playing a little trick on this component of the polarization vector. So alpha runs over xyz components, and p alpha is just one component of the polarization vector. And you can use a little differentiation by parts trick to rewrite the p alpha as the sum, or rather the difference of these two pieces. So the validity of this identity of this trick can be checked quite simply, and I encourage you to spend some time doing that. And according to our initial definition, this minus divergence of the p equals the polarization charge density rho. So let me just substitute that expression. Uh, and now the meaning of the integral of this second expression is quite obvious, because this is integral of position multiplied by the charge density, which is the classic definition of dipole moment. So the interpretation of this second term in the integral is that you're computing this dipole moment density throughout the entire volume of the dielectric, and the result is the bulk dipole moment. That's a very natural interpretation. So by applying an electric field, you create all of these little microscopic dipole moments inside the dielectric material, and the sum of that is obviously the bulk dipole moment of that material. Now, a much trickier part is the first integral of this divergence thing, and because this is a divergence of some vector thing, you can convert it to the surface integral again by invoking the Gauss theorem. Now you realize that this particular combination of P dot ds, where ds is the vector surface area element, this expression keeps popping up. We just saw this expression like 3 minutes ago when we were doing the integral of the divergence of the polarization vector. And here we have that expression popping up again, only with this extra weight of the coordinate vector. So this suggests that maybe we should be more careful to make a clear interpretation of what this quantity really means. Again, to make an interpretation, we need to make a little picture. And once you have a picture, then it becomes rather easy to make a physical interpretation of that quantity. Okay, so for convenience, let's imagine the situation where the p vectors are pointing outward, normal to the surface like this. Okay. Now, if this were the situation, then these negative charges that are slightly inside the surface will be compensated for by the dipole moment in the next layer, which means the only charges that survive are the ones that live at the very surface. These positive charges cannot be compensated for, because once you step outside the boundary, there's nothing. There's no charges to polarize and to cancel out these positive charges accumulated on the surface. So these positive charges that accumulated on the surface do survive the cancellation. And that gives rise to a rather nice interpretation of this inner product of P with a normal vector. So this n vector is the vector going outward in the normal direction from the surface. And according to this picture, if this inner product is positive, it means that there's some positive charge density being accumulated right on the surface. So this inner product I will call the surface polarization charge density. And with that interpretation, I can convert this surface integral expression to something that looks rather physically transparent. That is, it's the coordinate multiplied by the surface charge density. So x alpha is the coordinate of this surface point at which there exists this surface charge density sigma p. So again, this has the form of the charge density multiplied by its coordinate, which has the interpretation of being a dipole moment. However, this time this is a dipole moment due to the charges that are sitting on the surface of the dielectric, whereas in the previous case, we were looking at the dipole moment due to the polarization that live inside the bulk. So what this little vector manipulation has done for us is to separate the overall contribution to the dipole moment of that dielectric matter as the sum of the bulk contribution and the surface contribution. And each contribution is captured by its own respective integral forms. This is the surface contribution, and then this will be the bulk contribution. Okay, so now we have learned something about how to make sense of this surface integral p dot ds. But armed with that new understanding, let's go back to the earlier integral we performed for the divergence of the polarization vector. And this time we will try to think through this more carefully and more critically. So once again, by Gauss theorem, this conversion from bulk to the surface integral should hold. And earlier I said that why not extend this surface, Gaussian integration surface, out to a very large distance where polarization obviously does not exist. But one should be careful in applying the Gauss theorem that you can only apply the theorem if you're living in the region where P, the vector field on which you're applying the Gauss theorem, is continuous. However, polarization vector is not continuous, rather it's discontinuous across the surface. And a picture that proves my point is the following. Let's say you have a dielectric matter on the left side like this, with the polarization vectors all pointing to the right like that. But this arrows eventually has to terminate at the surface. And once you go outside the boundary, then there's nothing, there's no charge, and therefore there's no polarization. So from this picture, you can see that the polarization vector is finite all the way to the surface, and then suddenly it drops down to 0. So P is discontinuous. And you cannot, it's illegal to deform the Gaussian surface through the region where the function becomes discontinuous. And that means the trick of converting the volume integral to the surface integral will only be valid if your Gaussian surface remains entirely within the dielectric matter. It's just illegal to extend the Gaussian surface to the region outside the surface, because then you will be passing through the region where the function you're integrating has a discontinuity. So now the plan is to stop extending the Gaussian surface right at the boundary of the actual dielectric matter. Well, if you stop there, then this surface integral has a nice clean interpretation in terms, since we have just figured out that this inner product of the P with the surface normal vector is nothing but the surface charge density. This has a nice interpretation of the integral of the surface charge density over the entire surface of the dielectric. And that's just nothing but the total polarization charge that are induced, that exist uh, in the particular dielectric matter. So earlier I made a claim that dielectric matter cannot possibly possess a net polarization charge. But it turns out that claim was based on a mistaken application of the Gauss theorem. If you apply the Gauss theorem in the correct way and make proper interpretation of what this surface integral means, then a new conclusion is reached that the dielectric matter can indeed possess net electric charge, and that's the correct conclusion after all. So the reason maybe that I went through this whole exposition in this pretty roundabout manner is to perhaps convince you that vector analysis is never simple, especially in analysis of electrostatics, in the electrodynamics in general. And one should be always careful in knowing exactly what one is doing without supporting the mathematical physics with sound physical argument and physical intuition. You can always fall into trap and make errors that are not physically correct. Okay.